minus y square by 2 dy. But the integral of this v is, we know that it is equal to minus e to the minus y square by 2 actually. So this is what the integral of it is. And I'll just substitute the values into the integral. So if you're going to substitute the values into the integral, so the first term is going to be sigma square over square root of 2 pi. Okay. So the first term is going to be uv, so which is y minus e to the minus y square by 2, and substitute the limit minus infinity to plus infinity. Okay. And minus v du, so minus infinity to plus infinity, and v is really what do you call minus y square by 2, so this would be plus, so e to the y square, e to the minus y square by 2 and dy. This is what it is going to be. Okay. So I hope we got it correctly. So v is e to the minus dy square by d, and du is really dy. So yeah. So let's simplify this guy now. So I have this function y by e to the y square by 2. Then I want to take the limit y goes to plus infinity. So if I take this, okay, it's infinity by infinity form. So I can apply the, what do you call, L'Hopital rule. So this is going to be 1 divided by the derivative of e to the y square by 2, in other words y times e to the y square by 2, something like that, and that will go to 0 as y goes to infinity. Okay. You can also see actually that e to the y square by 2 greater way faster than y actually. So it just grows exponentially, faster than y. So the denominator is getting bigger and bigger while the numerator is growing slowly. So for sure this is going to go to 0. And same is the case if you take, say for example, minus infinity. The same conclusion will arrive. So you're going to get what? You're going to get this goes to 0. Okay. So now what remains is really this guy. Okay. But this guy, we know that this is equal to square root of 2 pi. So if you simplify, but don't forget about this plus mu square as well, okay, because this term is there. So if you simplify this term, so you have sigma square by 2 pi multiplied by square root of 2 pi. So the square root of 2 pi gets cancelled, and okay, so what this quantity would be is going to be, let me write it, sigma square by square root of 2 pi times square root of 2 pi in 0 plus square root of 2 pi plus mu square. Okay. So this guy and this guy will be cancelled. So what you get is mu square plus sigma square. And what all this competition was for. So this was really the expectation of x square. So we computed the expectation of x square. So what would be the variance of it actually? The variance of x is expectation of x square in sigma square plus mu square minus what? Minus minus expectation of x whole square, but the expectation of x is mu, so this is going to be mu square. So this will cancel out mu square and mu square, so you're going to get what do you call variance of x to be sigma square actually. Okay. So finally, what did we got? So if x is normally distributed, expectation of x is mu and the variance of x is sigma square. Okay. So these are the two crucial properties. Okay. Let's do some more bits of final bits of probability distribution, normal distribution, mathematics of normal distribution. I hope the calculations are making sense to you. My calculations are a bit different from the bookish calculation, but you can follow anyone. Mine or the bookish one, doesn't matter. Okay. So now, after normal, another most important version of normal distribution is the standard normal distribution actually. Standard normal distribution. So what do you mean by that? So a normally distributed random variable is said to follow a standard normal distribution if mu is 1 and sigma square, if mu is 0 and sigma square is 1. In other words, the sigma is 1. In other words, if x follows if x is normally distributed with mean 0 and variance 1, you're going to call it the standard normal distribution actually. Okay? And you have to also always keep the PDF of a standard normal distribution as well. By the way, whenever we have to denote something by standard normal distribution, okay, we call that as Z. Okay, so the standard symbol for a standard normal distribution is Z. Okay, so we call it Z. So what is the PDF of Z? So in your formula for standard normal distribution, substitute mu equal to 0 and sigma equal to 1. So you're going to get e to the minus x square by 2, because mu is 0 and sigma is 1, divided by square root of 2 pi. Obviously, x can be anything between minus infinity to infinity. This is what the standard normal distribution is. Standard normal distribution plays a pivotal role. Why it plays a pivotal role, I'll just talk in a moment about it actually. If x is a normally distributed random variable with mean mu and variance sigma square, then every x that is normally distributed with variance mu and sigma square can be written as mu plus sigma z. Every standard normal distribution can be written in the terms of every normal distribution with any parameter can be expressed in the terms of normal distribution, standard normal distribution actually. Okay. And how can I show that this side is really standard normal distribution? So let's compute the expectation of x So the expectation of x is really the expectation of mu plus sigma times expectation of z. And mu is a constant, so it's going to be mu plus sigma times what is expectation of z. So the z is normally distributed with mean 0. So this is equal to, what do we call 0? So it's going to be mu actually. So lucky expectation of x turns out to be mu. And what? And what would be the variance of this random variable x? You can also say if z is a standard normal distribution, a standard normal random variable, and you multiply it with sigma and add mu into it and give that guy a name x, then x is normally distributed with mean, mu and sigma square actually. So they can be, in other words, any kind of non-standard normal random variable can be written as in the terms of the standard normal random variable actually. So what would be the variance of x, for example, if you want to compute? So it's going to be the variance of mu, which is 0, plus the variance of sigma z. And sigma is a number, if I pull it out, it's going to be sigma square. And what is variance? So what is going to remain is variance of z. But what is variance of the standard normal? So it's going to be really sigma square. It's really sigma square actually. So what follows from here? So the key thing that you have to keep. So as I said, these are one of the key things that you have to keep in your head. This is one of the key things that you have to keep in your head. So if the key fact that you have to keep in head is if x is normally distributed with mean, mu and sigma square, we can turn this normally distributed random variable into a standard normal random variable by standardizing it. And what do I mean by standardizing it? That you subtract mu and divide by sigma. So if you subtract mu and divide by sigma, this would be a standard normal random variable, which is same as this actually. So this is called standardizing the normal distribution or the normal random variable. Normal random variable. Okay, you want to standardize a normal random variable? Just subtract mean and divide by sigma. And why you want to standardize it? We will show in a minute that it is very easy to do calculation with the standard normal random variable. It's very easy to do calculations with the standard normal random variable actually. Okay? Okay, so this is another important fact that you have to keep in head. So these are important things, star things that you have to keep in head. This is another important thing. This is another important thing that you have to keep in head. Now, let's talk about another fact that I would like to talk about. Fact, and I'll prove it actually. Suppose, which is relevant to this actually, doesn't matter. Suppose x is a standard, not a standard, but a normally distributed random variable with mu and value sigma square actually. And I take a linearization of x actually. So ax plus b. So consider this random variable. The question is, what is distribution of y? Okay. So let's compute the distribution of y. I want to do the all messy mathematics today about normal distribution and list all the key facts, and I want to use them later to, solve the problems. So, how to compute the distribution? If you know the distribution of x, how to compute the distribution of a function of x? So we, saw the trick actually. That okay, let's try to compute, say, the CDF of this normally distributed random variable, this random variable y. So fy of x is what is equal to this. So fy of x is by definition, what is the probability that y is less than or equal to x? Okay? And by definition, y is really ax plus b less than or equal to x. So I can express these probabilities in the terms of y, so you're going to get x less than or equal to x minus b by a. And so we wrote this probability in the terms of this. And what is this? This is really fx of the CDF of x, and we know about x actually. X is a standard normally distributed random variable evaluated at x minus b upon a. This is what the CDF is going to be. And if you want to find the PDF of y, differentiate both sides with respect to x. So if you're going to differentiate both sides with respect to x, this will become fy of x. This will become what? fx evaluated at x minus b upon a multiplied by the derivative of x minus b upon a with respect to x actually. So it's going to be what? So it's going to be 1 over a. Okay. Now we know the formula for fx of x. So fx of x is e to the minus x minus mu square over by sigma over 2 and the square root of what we call 2 pi and sigma. So this is what the formula of this is. So if I substitute x minus b over into this formula, so what are you going to get? So if you simplify this, you're going to get you're going to get what? You're going to get 1 over the square root of 2 pi a multiplied by sigma, so it's going to be a sigma, and e to the minus x minus b upon sigma minus mu chi square and everything divided by 2. Everything divided by 2 sigma square. This is what that you're going to get. Yes. This is what that you're going to get. So this is a actually. Okay. So if you simplify this a bit further, so you're going to get 1 over 2 pi a sigma, and you say that okay, you have x. So if you simplify it a bit more, so it's going to be minus x minus b minus mu square over 2a square sigma square. Okay? And let's do now something interesting. Let me give a name sigma prime quantity a sigma. So let's call a sigma as sigma prime actually. And let me call mu prime as b plus mu. And let's simplify this expression. So we can get 1 over square root of 2 pi. Okay. And what do you call this? A sigma will become sigma prime. ठीक है. So this prime is not derivative wala prime, so it's just a symbol actually. So it's going to be e to the minus x minus mu prime by 2 sigma prime square actually. This is what that you're going to get. ठीक है. Now if I ask from you, okay, what is the PDF? So whose distribution, oh, okay, this is a PDF of something, some random variable. What is, whose PDF is, किस random variable का ये PDF है? This is what they're talking about. Then you can say that, aha, this is basically, ठीक है, so this is equal to what you call fy of x. तो इसका क्या मतलब हुआ? So इसका मतलब ये है कि y is normally distributed with mean mu prime and sigma prime square. In other words, y is normally distributed with, अगर मैं वैल्यू सब्स्टिट्यूट करूँ, mu prime यानी b plus mu, ठीक है, b plus mu, b plus a mu, yes, we are forgetting something, a mu, a mu, b plus a mu, and sigma square यानी a sigma square. So let me summarize what I have done. This is another fact that I would like to, what you call, write, and I want you to keep it in your head actually. You can keep it as a theorem or whatever. So if x is normally distributed with mean mu and variance sigma square, then ax plus b is normally distributed with mean a mu plus b and variance a sigma square. So this is an important fact that you have to keep in mind. And it makes sense actually. Think about it. अगर आप expectation compute करें ax plus b की तो वो क्या होगा? So I can say this is same as expectation of x plus b. So a और x की expectation क्या है? Mu. So it's going to be a mu plus b. If you compute variance of ax plus b, so it's going to be variance of ax plus b की variance is going to be 0. So you can pull this a out and you're going to get what we call a square, and variance of x is going to be sigma square actually. Okay. So it makes sense actually. So if you have a linear expression of a normally distributed random variable that is also normally distributed. Okay. Alright, so this is another fact. So the last thing that I would like to talk about is some properties of standard normal distribution actually. Standard normal distribution. So remember, Z is going to be standard normal if it is normally distributed with parameter mu 0 and 1. And the PDF of a standard normal distribution is e to what? E to the minus x square by 2 over x to the power of 2 pi. This is what the standard normal distribution. Now, what is the CDF of a standard normal distribution? By the way, usually standard normal के PDF को small phi of x से भी represent किया जाता है. We also write it as small phi of x. ठीक है? To write the standard normal distribution. Or what would be the CDF of standard normal distribution? The CDF of a standard normal distribution is going to be phi of x. ठीक है, और phi of x क्या है? Obviously this is probability that z is less than or equal to x, which is same as that you integrate from minus infinity to x what this e to the minus say y square by 2 over square root of 2 pi dy. Trouble with this integral is that you can't solve it integrally. Okay, you can't solve it analytically. You can't solve it analytically. So what you have to do, you have to solve this integral numerically. Okay. Integral must exist because this is a continuous and bounded function. So there is no doubt that this integral would exist. But what you have to do is that you have to kind of solve this integral numerically for every x. So in other words, if you want to compute phi of say 1, so you have to do minus infinity to 1 e to the minus y square by 2 square root of 2 pi and dy. Okay, solve it numerically and you're going to get some answer. But do I have to always solve it numerically? The answer is no. So what you will find most of the time आपको क्या मिलेगा? That कि अगर आपको standard normal CDF, what you will have a table of standard normal CDF. Table of standard normal CDF. ठीक है? So if you see that, for example, page number 201 page देखें of book, you will find a table of a standard normal CDF. अच्छा, interestingly, the table of a standard normal CDF goes like this actually. So उसमें आपको दो नजर आएंगी values. So you're going to have x here, or you will have here like this, okay, so 0.1, 0.1, 0.2, 0.3, up to say 0.9, और उसके बाद you will see that you will have obviously 1.0, 1.1, and so on and so forth, and the table goes on. For example, you know, the book में given है it's 3.4. You can go even more, but 3.4. ठीक है. So column में होंगी ये रखी हुई, और रो में ये रखा होगा. So 0.00, 0.01, 0.02, 0.03, and so on and so forth, 0.09. ठीक है, so you're going to find this actually. अब यूज कैसे करें इस टेबल को? तरीका क्या है? फॉर एग्जाम्पल मुझे कंप्यूट करना है phi of 1.23. ठीक है जी, 1.23 या 1.13. So imagine I want to compute phi of 1.13. ठीक है, यानी मैं ये मालूम करना चाहता हूँ क्या चांसेस हैं कि जी the standard normal random variable has a value less than or equal to 1.13. This is what that I would like to do. तो मैं क्या करूँगा, इस टेबल में जाऊँगा और सबसे पहले पहुँचूँगा कहाँ पर 1.1, और उसके बाद में पहुँचूँगा फॉर एग्जाम्पल यहाँ से लूँगा 0.3. So this is going to be the value. ठीक है, so 1 point plus 0.3, so it's going to be 1.1. फिर यहाँ पर जो भी नंबर लिखा हुआ है, so someone has already calculated some numbers for you. ठीक है, so for example 1.1 13 here is 0.9049. 0.9049. ठीक है, so this is the probability of phi of 1.13. अगर आपको चाहिए for example phi of 2.32, then you know how to do it. कि अच्छा आप जाएंगे 2.3 पहला